Hello, everyone. This is Cognitive Science 508 at Middle East Technical University. We are covering a range of topics that are relevant to cognitive science. And today's topic is about artificial intelligence. And this is a 1 hour introduction to artificial intelligence. Instead of breezing through every technique in AI or what it's trying to do, I'll just give you a summary of everything in one shot, and I'll just go over them one by one to give you a sort of a sense of situation of AI in cognitive science and the kind of things that we do in artificial intelligence. I'm Jim Bosshine. And I speak to you as someone who's done a PhD in artificial intelligence and then moved on to cognitive science and linguistics. And I had done that as a computer scientist in computer science department. So I speak from experience in connecting language, planning, artificial intelligence, from the perspective of cognitive science, including the modeling and theories. I thought I'll first give you a sort of an appreciation of what we are trying to do in artificial intelligence and where it got at this point. In cognitive science, when you look at cognitive problems that we face, you can think of simple behavior, and you can also think of complex behavior. I mean cognitive behavior like planned action, language, dancing, planning, music, inference, thinking, vision. These sort of high-level processes, you can think of them as showing some simple behavior, and some of them are complex behavior in the sense of not being able to sort of disentangle the parts and say these are the components, and you just put them together and you get AI. This is complex behavior is complex mainly first because of its size, and two, because of its internal structure that's difficult to disentangle about who does what and how things come together to all these things. You can think of simple behavior and complex behavior in that respect. Of course, in cognitive science, you're dealing with mechanisms. So when you talk about mechanisms, mechanism is just is another way of saying we're interested in how things are done. That's the idea of mechanism since Newton. So that's so we're not talking about machines with lots of gears and all that stuff. Mechanism means we're interested in the how question. So these mechanisms can be quite simple or they can be quite complex. And you can, of course, study. So the point is, you study mechanism, you study the behavior. That's what's observable, and you under the guidance of some mechanism and building a model over top of that mechanism. So if you're dealing with simple behavior and using a simple mechanism, yes, that's very fine and conservative, and that's probably good. But we know that most of this behavior that is worth studying is complex. So this is not going to sort of give you a sensation of AI, just doing simple behavior with simple mechanisms. And then you can say, of course, this one is a bit of a sort of a questionable connection If you have simple behavior and you're dealing with it using very complex mechanisms, then there is something missing here, because after all, the behavior is simple enough, but your proposal for doing that is very complex. So that's not going to give you an understanding of the phenomenon. Disconnection. If you have a complex behavior and you're studying it sometimes equally complex mechanisms, that's not really our notion of understanding a problem. Usually, when you understand a problem, the kind of behavior that you understand is sort of couched into terms that are simpler than the behavior itself. So the mechanism is supposed to be not as complex as the behavior itself. Okay. So the critical connection that we try and emphasize in AI is this connection. Can we really study very complex behavior using simple mechanisms? Simple in the sense that although the behavior gets more and more complex, the underlying mechanisms remains to be simple. We just need more and more models of things to sit on top of this simple mechanism to give you the complex behavior. So that is the interesting connection. And you can see this history of doing that in the history of AI. In some sense, AI started with Turing's challenge after the Second World War. Alan Turing basically, after having built some computers, he wrote an article about computers and mind, and basically suggesting that, look, you can do this connection. It's a very simple mechanism with very complex behavior. And then if you keep doing that, then there is no telling where you're going to stop understanding complex behavior. You seem to be able to build maybe as complex as the mind itself using very simple mechanisms. In this case, of course, the idea of a computer. So the computers are very simple mechanisms, right? I mean, you can build very sophisticated programs, you can build very sophisticated architectures, but the mechanics of the computer itself is very simple. And the mathematical formulation, also by Alan Turing, was in fact mathematically very elegant, but besides mathematical elegance, it was shown to be so extremely simple. Just a finite set of states and a memory that you can go back and forth to be able to do any kind of computable function. And this is a very simple mechanism in computer science terminology. So that's a sort of an implicit sort of claim that what appears to be so complex as a behavior is arising from very simple mechanism. Led to different kinds of goals in AI ever since 1950s. So one brand of AI is called weak artificial intelligence, sometimes called technological AI. The idea is to say, well, we are trying to make this model. We want to attack complex problems. We want to be able to make tools that try these models. But we're not going to make any claims about whether these models themselves constitute an explanation for what we call this complex behavior of mind. So there's this assumption that in AI, that's almost everyone subscribes automatically, sort of like computational theory of mind. If you're working on sort of modeling of the mind, and if you're doing it using AI techniques, that's because you're saying the idea of a computer as a simple mechanism might be enough to give you complex behavior. So weak AI is not saying that. Weak AI is not saying that complex behavior constitutes itself as a theory of how organized action, planning, language works, but it does model the phenomenon to the extent that you can build systems that are sometimes indistinguishable from like human performance. Strong AI. This is a term from 80s. is taken to be the claim that once you build a model of that complexity from a simplicity, then that constitutes as an explanation uh, for understanding complex behavior. So when you take AI this way, the strong AI way, you're basically saying that you can not only build complex models of complex behavior, you're also claiming that these complex models themselves constitute some kind of an artificial mind. So you can build, not only you can understand the mind using AI techniques, you can build artificial minds using AI techniques. um, so this is sort of different takes on AI that we have seen ever since its inception in 1950s to this day. One sort of game changer in this was David Marr in 70s, where he said, like, look, we're dealing with complex information processing problems, and artificial intelligence programs are meant to take on these complex information processing problems, but they're not doing it in a very ordinary fashion. They are doing it in a way that sort of that allows you to clearly define the problem, clearly define the limits of what you can do, clearly define its algorithms, clearly define the kind of substrate that it can run on, and try to connect this to to a level of explanation where you say, look, these sort of algorithms and substrate are trying to do this as a goal of this problem solving. So he famously suggested in 1977 that instead of AI taking on any kind of problem, ill-defined problems, sort of open-ended problems, he said, well, we should try and define um, some problems to the extent that we can study them in so much detail uh, that, and the only way we can do this in so much detail is if you allow them to give you a sort of an algorithmic level, like what is your data structures, what are your algorithms, what is it that is supposed to do, what are the limits of this, and then mapping of these algorithms, knowledge representation, and others to a substrate that can execute these things, and then taking these two and connecting it to what you call the computational level. So his levels were like three: computational level, algorithmic level, and at the bottom was the substrate level. And he famously suggested that not all AI problems are going to lead to to what is called a type 1 theory. In other words, a type 1 theory is, in Mark terminology, is like it's a complex. It's the understanding of a complex information processing problem at all levels, with connecting theories between these levels to the extent that at the top level, at the what you call the computational level, like goals and function, and these things can also be clearly defined so that you can see, well, yes, that looks more like an explanation rather than just a whole bunch of algorithms running around. So there was so when you look at many sort of well worked out AI problems, they are more like Mark kind of problems. That is, they were able. We were able to define them at the level of algorithms. We were very clear about what kind of substrate can run these algorithms. We were not always able to connect them to top level of Mark, because there wasn't always an explanatory theory for these things, but we've gone far enough in vision and planning and language to be able to tackle these complex information problems using basically AI techniques. So that's essentially how AI started. It's not just simply let's do arithmetic. People are very bad with arithmetic. Um, Computers do that better, and let's call that AI. That's not the idea. The idea is we're having a complex problem here, and we're trying to understand this problem by dissecting it using representations, algorithms, substrate, goals, functions, and bridge laws between them. So that's the sort of AI take on a difficult problem. So the way we do this in AI has come to sort of to present itself at least in several dimensions. So one critical thing, at least for the middle level, is well, what kind of things you're going to operate on? What is your knowledge? What constitutes knowledge in your domain? How are you going to represent this knowledge? How are you going to, have um, um, data structures and algorithms that manipulate this knowledge? This kind of thing. This is a huge field, and a good deal of work in AI depended on having the right kind of knowledge representation for the problem, and that's still a sort of a black art essentially. And of course, if your problem is complex enough, you're going to need some kind of search. Search meaning the solution space is quite large, and you want to narrow down your search for solutions in such a way that it can be called intelligent in some sense. In fact, Newell and Simon uh, uh, proposed physical symbol hypothesis in the 1970s as saying, well, search and knowledge representation is and doing that in general domains that we call cognitive is the mark of the cognitive behavior. So search comes in various forms. If there is, if you know the goal, you can, from current state to the goal, you can work different ways. For instance, you can work your way back from goal to the current state. This is called backward reasoning. You can go from current state to the goal. This is called forward reasoning. Assuming you have the goal, you know the goal. If you don't know the goal, then the search becomes something like, well, but why don't I just prune the search in such a way that, although I don't know the goal, because of the current state that I'm in, I can sort of narrow down where I'm looking at next, and so I can. So depending on the nature of the problem, search can be very algorithmic, or it could be very heuristic. And some of the things that we used to think as heuristics turned out to be actually algorithms, like the A-star search algorithm, turned out to be optimal given certain conditions, which you can learn in classical AI books. And all of that is in aid of problem solving. In other words, you have certain current states of the world, and there is a certain goal, like joint problem solving, going somewhere, or understanding an expression, or going through the maze, understanding physical limits, physical understanding like rigidity, permeability, things like this. All of these essentially combine. So problem solving essentially is a sort of combining various techniques from knowledge representation and search to be able to attempt problems. So these are classical domains in AI, and I'm not going to go into detail because actually there are courses specifically designed for every one of these. So I'm just giving you a flavor of why we're trying to put many things together to tackle these problems in a fashion that says, well, yes, I am working on a non-trivial problem, and I'm working on it with the kind of tools that I can control in modeling to the extent that I know the complexity of the mechanism does not increase as the complexity of my model increases. so that I can, manipulate the modeling using that simple mechanism. So this whole practice of having simple mechanism, complex behavior is pretty much reflected in all fields of AI. And they develop their own techniques, and some of them are quite ingenious. So I'm going to, there are courses for these. So machine learning, um, um, in the early days, it was first like a very symbolic learning of these knowledge representations, learning of how to search, how to narrow down search. That's how it started. And then came this parallel distributed processing approach, which said, well, when you look at associations between input and output, there are many things you can learn about what goes on in between. And then machine learning took a new turn in 21st century, essentially, by taking, coming up with ways to manipulate huge amounts of data with somewhat sort of simple knowledge representation techniques like vectors, matrices, and instead of doing a lot of sort of what used to be called like feature engineering, what does this knowledge representation need? Well, it needs these features, that feature, and then if that doesn't work, then your problem performance does not scale up because the features that you selected began to sort of to constrain you. So machine learning essentially made a breakthrough by saying, well, I can manipulate large amounts of data using very simple knowledge representation mechanisms like vectors and others, and that's going to give me performance to the extent that, for instance, at this point, the artificial Go player beats the Go champion. So these essentially are the things that made machine learning sort of so popular in AI. Well, of course, all of that connects to uncertainty in the way that in all of these things you take some computational steps, and all of these steps essentially can be, in principle, non-deterministic. And how do you deal with that non-determinism? Non-determinism can be manifested in two ways. First of all, non-determinism is essentially very much part of the data. The data itself is open to interpretations, or even if the data is sort of well understood and well represented, the way you manipulate that may contain some non-determinism itself. So you have to deal with these kinds of uncertainty in the data, uncertainty in the inference, uncertainty in the computation, and that sort of thing. So this is sort of you can tell a good AI program by seeing how well it sort of it integrates all these methods into some kind of of behavior that seems to be rising above data. So this is more than data. We're not doing like 3 and 5 plus 8, 3 and 5, 3 plus 5 equals 8. This is more than that. So it's this sort of intelligent combination of these techniques with the goal of solving complex information problems with an attempt to clearly define them is giving you sort of the edge, essentially, in making AI programs more and more successful. And of course, every success comes with some questioning. It's at this point, if you look at AI, I mean, back in the 70s and 80s when I was a student, AI was something that you do in weird corners of universities, in strange labs that work at midnight, and a bunch of nerds coding along. And it was essentially sort of a university activity. Um, but because of success of machine learning and our handling of uncertainty, to a certain extent, um, uh, it became part of our lives in a sense. So if you look at like classical AI books, they will say, well, first there was this blooming of AI. Like after Turing, there was this energy to say, well, let's tackle all these problems using knowledge representation, search, and there were so many grants about AI, and there were very strong promises made by the researchers. Um, most of these promises were not met. So and they were mostly over promises, and there was something called the AI winter had happened. Basically, the funding for AI began to sort of die down because essentially AI researchers were not delivering what they promised. And then that changed because of our computational power. I said, well, yes, we're going to, instead of, working with brittle knowledge representations, things that only work in toy domains but that does not scale up to other things, why don't we just have, a more sort of um, uh, computation-friendly representations like vectors and matrices, which you can manipulate all the different ways. And we can start, instead of having to worry about like, but this feature is needed for that problem, that feature is needed for that problem, but it's the same kind of problem. Why are we having these features? Instead of worrying about this, you began to see things like end-to-end functionality from AI programs. You feed in data, you gotta get some complex response out of it, and that's mostly because of incredibly powerful um, uh, manipulations of data in between, without having to worry about human intervention. That's called end-to-end sort of modeling in AI. So that was the game changer. But because of that success, because of the computational power, um, uh, if you're not an AI practitioner now, I don't think it's not enough anymore to know just the techniques. I mean, you can talk to anyone. Just get on a public bus and start talking to anyone from 10-year-old to 80-year-old. They have some ideas about AI now. That was completely unthinkable 20 years ago. um, so essentially, it has become um, uh, something of public interest. That's mainly because it affects their lives. So you need to know, I think, at this point, a lot more about AI than just the techniques. You need to know where this is going, um, um, the ethics of AI, so to speak, in a digital world. Um, um, and that's mainly because although AI was a public object, I mean, it's been talked about for a long time, it has become a public subject. I mean, people think these programs that do wonderful things for them. I mean, if your mobile phone is essentially your daily organizer, it can do many things. And when it begins to do many things. It gives you reminders. It tells you to do this. You say, well, you haven't walked enough steps today, so why don't you exercise? Things like this. You begin to think, well, maybe it's intelligent. Maybe it's just and although what it's doing is just multiplying a whole bunch of numbers, you begin to treat it as some kind of like a subject, not just an object. So when you begin to do that as a user in daily life, then AI takes a whole new turn. Now, although these algorithms are not making decisions by themselves, they were programmed to make decisions by the programmer. You begin to take them as if they are making their own decisions. You take it to your life in a way that you take, so like a sentient being. So Dennett, philosopher Daniel Dennett, called this the intentional stance. In other words, although these programs aren't really, don't have their own consciousness or free will or something like that, whatever you want to call it, if you begin to treat them as if they have one, then you're going to have a completely different take about uh, where this is going, whether this is really the algorithm that you think is just is as a sentient thing, um, is really doing the kind of decisions that humans make or animals make, others things with mind makes. You begin to um, uh, take AI on a different level when you assume it is part of your life. So even though people who know that AI is not, these AI programs aren't really like humans, uh, they are they tend to take it as if they are part of their lives, and they take decisions just like a subject, mainly because that's what's happening in their lives, and they have to live with the consequences of that, just like you deal with the consequences of having neighbors and relatives and friends and dogs and cats and things like this. So things are changing in AI, and it's becoming more and more a part of our lives. And I think in cognitive science, it's important for us to tell people, although this behavior is pretty complex, we're not really making the mechanism equally complex to match up with the expectation that's growing for AI. Okay, and of course, I'm not saying that this is how the computers work. This maybe the human mechanism is just as simple as well. But the point is when people take a different stance in the kind of program that you work, it puts a different kind of intellectual responsibility on you as an AI programmer about what you do with these things. So all those, 20 years ago, you can just think about sort of formal aspects of what you're doing, quality of your search and things like this. Now you need to worry about the consequences of what you're doing in action. And that, I think, calls for a sort of new way of thinking about AI, and but for you to be able to appreciate all that, I think you need to be well versed about these topics. And as you know, we have courses about almost all of these. Not, for instance, we have courses on this, we have courses on that, but not always exclusively. These are all covered in some course in some way. And we have philosophy of mind courses on this. So we're going to attack these problems and understand what we mean by AI. This is just a short introduction to what to expect from an AI program. So if you want to put all that in perspective and say, well, just give me an example, I can say, well, just take a problem and then just sort of artificial intelligence this problem, so to speak. What does it mean to have an AI take on the problem rather than just some other take? Well, it's one thing is and let's say the problem is going somewhere from here, or going somewhere from somewhere. And in this particular case, let's say I want to go from Ankara to Istanbul. Okay. So what's an AI take on this kind of problem? Well, if you're going to deal with it in sort of David Marr kind of way, then you can say, well, this is an instance of a complex problem of sort of like organized behavior. After all, there are many different ways to go from Ankara to Istanbul. I can try randomly and try and go to Istanbul. I go to the next town. Is this Istanbul? No. You go to the next town. Is this Istanbul? No. I can try this. And nobody's going to say, well, that's not a very intelligent way of going to Istanbul. And you can say, well, I can do more. This is like almost like reactor planning. You can say, well, I can do slightly more instrumental. I go to place. It's not Istanbul. Yes, I know, but it says something about Istanbul. So I take that knowledge into account, narrow down my search about where to go for next town, and keep doing this. But I never plan ahead from from my current state. I just make more informed decisions in my current state. This is sometimes called instrumental planning. For instance, you can do it like this, or you can conceive this problem as something like organized collaborative action. So if I want to go to Istanbul, I can say, well, I can buy a ticket for an airplane and fly and go to Istanbul. But for me to buy a ticket for Istanbul, somebody has to provide a service for selling tickets. So I'm going to find these services. I'm going to find these how they meet my criteria, dates and whatever. And then so say yes, I want to be at Istanbul. So from that backward, I say, well, I can fly, but for me to fly, I need a ticket. To have a ticket, I need to buy a ticket. To buy a ticket, I need some money and things like this. So you make some knowledge representations and search assumptions. At the same time, trying to solve a problem of getting to Istanbul. To get to Istanbul, I want to get to the airport first. Well, there are different ways to get to the airport. You can take the metro. You can take the shuttle. If you're going to take the shuttle, you're going to buy a ticket for the shuttle. Well, buying a ticket for the shuttle is a bit different than buying a ticket for the airport for the flight. So it's not just buying ticket, but buying ticket for the shuttle versus buying ticket for the flight. So you begin to make these distinctions and knowledge representations, and you begin to take it as a collaborative action, so that when a system built on this principle says, well, okay, here's a plan for you. Take this shuttle, be at the airport this time, take this flight, and you're in Istanbul, and while you're there, take the shuttle to go back to the city center. When a program gives you that, and the steps that you get in between begin to make sense to you rather than just random selections of things, you can bet on it that there is a bit of AI in that modeling of the problem. So that's usually how you treat a problem as a complex information problem with all its algorithms, data structures, things to run, means to run it, and what is the goal of this. If you can come to that level, of course, that's quite an explanatory value, but at least tackling a complex problem essentially means understanding how it can be well represented so that it can be well manipulated. So you're going to see all of that in about just about any course in cognitive science, and I guess I'll see you in some of these courses. Okay? So see you soon and stay safe.